All right, so what we're looking at here are limits toward infinity. So limits toward infinity are really important in calculus because these help us find out what the end behavior of the graph is. So where the graph is headed as x approaches both positive and negative infinity. A big thing to keep in mind is this idea of weight or pull of a function. And so this is a very non-scientific way of looking at how functions work, but a good rule of thumb is that exponentials tend to pull more than power functions. Power functions generally tend to pull more than logarithms, unless, of course, you're talking about maybe a constant function or something like that. Um, those are just guidelines. Keep those in the back of your mind as we're going through some of these examples. One of the most important things that you'll learn in calculus is how to handle rational functions, and that's going to be this idea of the limit as x approaches either positive infinity or negative infinity for something like f of x over g of x, where both f and g are polynomials. So what you're going to do whenever you encounter a rational function is compare the degrees of f and g. So if the degree in the top is greater than the degree in the bottom, the degree in the numerator is greater than the degree in the denominator, then the limit is going to diverge. And it's either going to diverge to positive infinity or negative infinity, just depending on the the nature of the function. So the second thing, though, is that if the degree in the top in the numerator is less than the degree in the denominator, then the limit will always converge to 0. And then the one that's a little tricky for some students is whenever the degrees in the top and the bottom are the same. So maybe you have a cubic function in the top and a cubic function in the bottom. If that's the case, then the limit is going to be determined by the leading coefficient in front of the term with the highest degree. So essentially what we're looking for whenever we're finding end behavior in rational functions is we're looking for horizontal asymptotes. If the function has a horizontal asymptote, then the limit as x goes to either positive or negative infinity will probably go toward that asymptote. So just a few quick examples of limits toward infinity for something like this. We have clearly rational functions, a polynomial in the top and in the bottom. In this case, the degree in the numerator is 3, the degree in the denominator is 4. So since the leading coefficient in front of x cubed in the top is 1, the leading coefficient in front of x cubed in the bottom is 4, my limit as x approaches infinity is 1/4. If you look at the second example, I have the limit as x approaches negative infinity for a linear function 1 minus x in the top divided by a quadratic x squared plus 2 in the bottom. The degree in the numerator is 1. The degree in the denominator is 2. So what that means is my horizontal asymptote is located at 0. So my limit as I approach negative infinity is also going to be 0. Notice the degree in the numerator is less than the degree in the denominator. In the last case here, I have x squared plus, or excuse me, x squared minus 1 divided by x minus 3. If I were to compare the degrees, the numerator has a degree of 2, the denominator has a degree of 1, so this means that my function is going to diverge. And in this case, it's going to go up to positive infinity. If I look at something maybe a little bit more complicated, maybe I want to find the limit as x approaches infinity for e to the x. So essentially what you do is you just plug infinity in for x. So e to the infinite power. So as x gets really, really large, as I increase the power of my exponent, so to the 10th power, to the 100th, to the 1000th, the 10,000th, so on and so on and so on and so on, my values of y are getting bigger and bigger and bigger. And eventually, as x approaches infinity, my y values will diverge to positive infinity. The cool thing here with the limit of e to the x as x approaches negative infinity is this. If I were to put infinity in the exponent, I would have e to the negative infinity. And we know that negative exponents create reciprocals. So really what this is e to the 1 divided by e to the infinite power. So as my values of x gets really, really large, my exponents continue to increase. So this is 1 divided by e to the 10th, 1 divided by e to the 100th, and so on and so on and so on. So the top is remaining 1. The bottom is getting bigger and bigger and bigger. So essentially what I'm doing is I'm creating smaller and smaller fractions. So eventually this is going to converge to 0. And remember that the exponential function e to the x has a horizontal asymptote at x equals 0. So as I go backward toward negative infinity, my y values will converge to that asymptote. Here's just a few more examples. If I have something like this where e to the x is divided by x squared, remember exponentials pull the function in a lot more powerful way than, say, a polynomial like x squared. So if I were to look at this, as my powers of x get really, really large, I'm taking something so like e to the 10th divided by 10 squared, e to the 100th divided by 100 squared, and so on and so on and so on. So the values in the top are growing much faster than the values in the bottom. So my limit here is going to diverge to positive infinity. If I look at this case where I have x squared over e to the x, and I'm looking at the limit as x approaches positive infinity, remember x squared grows slower than e to the x. So I'm getting something small in the top and something huge in the bottom. So this is creating smaller and smaller fractions. So my limit's going to converge to 0. In the case of limit as x approaches negative infinity for x squared over e to the x, what's happening here is I have x squared e to the x. So if I were to plug in a negative for my exponent, then what that does is it creates a reciprocal. So really what I'm looking at here is something like negative infinity squared over e to the negative infinity, which is what we have up here. So negative infinity squared times e to the infinity. So as my values of x get really, really large, so I'm squaring numbers and then multiplying them by e to the infinite power. So 10 squared plus e to the 10th, 100 squared times e to the 100th. These numbers are getting larger and larger and larger, and they're going to diverge to positive infinity. So just something to keep in mind, something divided by something really tiny gives you something really huge, where huge is infinity and tiny is really, really close to 0. So something divided by something really small gives you something really big. Something divided by something really huge gives you something really, really small. So something over tiny equals huge, and something over huge equals tiny, where huge is infinity and tiny is 0.